What's up guys, welcome to day 28 of May 2020 LeetCode challenge. So today's question is counting bits. It asks us to the problem statement is given a non-negative integer number num. For every number I in the range 0 to I to num, calculate the number of ones in binary representation and return them as an array. Okay, so there's this. All right, so basically the question is asking us to that we will be given a number num, and it's going to be, I think, does it say greater than 0? Right. So for every number in the range 0 to num, we basically need to calculate the number of ones for each of those numbers. So the number of ones in its binary representation. Okay, so for 2, so 2 is 0, which is 0 from if we check the range from 0 to 2, so 0 would have 0 ones in its binary representation, 1 would have 1, and then 2 would again have 1. And similarly for 5 we would have 0, 1 for 1, 2 for 2, 1, 2 for 3, 1 for 4, and 2 for 5. Okay, let's look at the follow-up now. It is very easy to come up with a solution with runtime of O of n size of integer multiplied by size of the integer. But can you do it in linear time, possibly in a single pass? Okay, and space complexity should be O of n. Alright, can you do it like a boss? Do it without using built-in functions like C++, such as pop count or similar. Alright, okay. So now we know that we need to count number of ones in the binary representation. We could essentially, and we need to return an array is also what we know. So let's dive in and let's try to first achieve this before we actually achieve O of n. So let's look at how we would solve this. So for each number, if we check if it's an odd number or an even number, that should be sufficient for us to count the number of ones that exist inside of its binary representation. Let's look at how we would do that. So we would start by having our array. The array, actually that was perfectly valid, but yeah, int num plus 1, and num plus 1 because we're going to be going from range 0 to the number. Now for int I is equal to 0, we don't start with 0, we'll start with 1. We don't start with 0 because we know there won't be any ones in the binary representation of 0. So, and by default all the elements inside of this array are initialized to 0, so we don't bother checking the 0. So I would be less than equal to number. Now we will have an integer which would be, say, res, and while our actually here let's put in n is equal to I. So while n is not equal to 0, we will increment res, but we will increment it when if n mod 2 is 1, and then we will remove the last significant bit. Once we're done, we will add this to our array, result array, at ith location the value of res, and we return result. Alright, let's run our code to see if it gives us the desired result. So for 2 it does that. Let's check for custom input for 5. And it gives us the expected answer. So this is a perfectly valid answer, but in a follow-up they ask us, so the complexity of this algorithm here is n multiplied by size of the integer. So now let's look at how we would come up with a linear solution with possibly in a single pass itself, and let's look at also how we can basically decrease the space complexity. Actually, the space complexity is of n only here, so that's what I'm going to keep, but let's comment out this code for now. Right, so I would like to bring to your attention here that actually let's uncomment. So our custom input is, let's take it for 2. So it says these are the values that we get from 2, right? So 2 can be represented in its power since we're working with binary representations. So 2 can be written as 2 to the power 0, which is 1, then 2 to the power 1, which is 2, and 2 to the power 2, which is 4, again 2 to the power 3, which is 8, and similarly 2 to the power 4, which is 16, 2 to the power 4, and so on. So what do we notice from this behavior? If we look here, the value of 2 is 1, but if I change this value to 3, I'll change it to 4 as well, so that we get both the values here. So you can have a look here that as soon as I do a 4, which is power of 2 as I mentioned here, the value, the number of ones resets itself to 1. So at 2 it was 1, at 3 it incremented by 1, and here it's again 1. Now if I were to take say 6 and 8, let's look at how they look. So you can see here 6 at value 2 is 1, the number of ones in the binary representation. Again, the number of ones in the binary representation is 1 at 4, and interestingly at 8 again it's 1. So we can notice that every power of 2, this value increments, and it basically, it resets itself to 1, and post which, if we have, so let's look here. So 3 can be written as 2 plus 1. 3 is equal to 2 plus 1, and its value basically now is the number of 2's, the number of 1's in the binary representation would be 1, which is from here, from the previous number, plus 1. So binary representation of 2 is this. So this value comes out to be 2, and that's the value for 3. Similarly for 5, I'm going to calculate it here. We haven't seen that, and let's see if I'm correct in my calculation. So 0 would be 0, then 1 would be 1, then 2 would be 1, then 3 would be 2, then 4 would again be 1, and then 5 would be 2. So how did I derive this is 4, the value is 1. For the number of ones in the binary representation is 1. Now 5 is 4 plus 1, so that is 2. Similarly 6 would be 4 plus 2, 6 4 plus 2, and the number of ones in 4 is 1, plus the number of ones in 2 is 1, so it's 2. So that would be for 6. So if I were to represent 6, then 6 would be 6 equal to 0, 1, 1, 2, 1, 2, 2. And I think we just calculated for 6, which it is the same. So I'll just copy it up here so you can have a look. So it's the same value as you can see here. So this is the intuition behind it, that every value of power of 2 that we encounter, the value of number of ones resets itself to 1, and then there is a number x after it. So for here, for example, here for 5, so for 5, as I represented it before, it is 4 plus 1. So generalizing, it would be 2 to the power of a variable power of 2 maybe, and plus x. So whatever this x is, we would have actually pre-calculated it, and we would have to constantly keep on calculating it. We just have to add it to that previous value of 2 to the power whatever that power value is. So let's look at how do we implement this in code. We would still need the same for loop, but I am going to add 2 more variables here, as you can see from up here. Where is it? Yeah, the power of 2 and x. These are the 2 values that we're going to be working with. So int power of 2, which would be 1 initially for starters. We won't be considering we won't be considering anything else, because we know 1 would be 1. So what we're going to do here is we will have an x also, which initially would be 1. Now we're going to check if, so let's look here, if x I is equal to power of 2, so power of 2 would be actually any value which is power of 2, so not 2 to the power of 2. So if I is equal to power of 2, which is 2, 4, 8, 16, 32, and so on and so forth, we will add 1 to the result at ith index, and we will reset it to 1. Then power of 2, this is how we can calculate the next power of 2, and we will reset the value of x to 1 again. Otherwise, result I is equal to result, and this value will be the x value plus 1. So and then we're going to do an x plus plus, or I can simply just write it here plus plus, and then we simply return result, and that will give us the desired result. Let's run and check. Okay, I didn't define this. Right. Typos. And we get the desired result. So this is how now the complexity has come down to O of n, and our space complexity is also O of n. Let's quickly just submit it also once. And it has been accepted. We've passed 15 of 15 test cases at runtime and 1 ms, and we're beating nearly 100% of the submissions. Thank you guys for watching the video. I hope this helped you understand the intuition behind counting bits. Do press the thumbs up button, subscribe if you've already not subscribed, and press the bell icon. I'll at least be posting one video per day. I am trying at least. Thank you.